recording. Okay. Oh. And I will give one more example for this. So let's say example. Let's say we have a system like this. Let's say we have a string K. We have a bar that is massless, supposedly. At one end, you have a mass. So this is A and this is B. This might be the middle O, let's say. This distance is A and this distance is B. The displacement here, we call it XA. And the displacement there, we call it XB. So this is a rigid bar. It has no mass. Now we can reduce this to a mass and spring system, okay? For example, you can do the following. If you want to you see that the coordinates XA and XB are related, okay? You can see that XB over XA is equal to, what can you say? B over A, right? Yes. From here, actually, BB over VA velocities are also proportional. So, if you want to model things at A completely, well, at A you have a spring K, that is the same spring. There will be a equivalent mass here. And this will be XA, mass equivalent at A, let's say. Okay. We can find the the displacement. We will find the equivalent mass. Equivalent spring is K here. There is no difference. But if you want to model it at B, that will be kind of different because there you will have a equivalent spring. Because the spring will be different. K equivalent at B, let's say, and this will be M. This is the kinematic relationship between A and B. Okay. XA times B, XB times A. Yes. Okay. Now, if you want to model it at A, this one, you will usually use the kinetic energy of the system. Kinetic energy will be 1 over 2 m A. There is no mass there, but m equivalent at A, BA squared would be 1 over 2 m. The mass is there, so mVB squared. So, and since VB over VA is equal to B over A, we can write the following. 1 over 2 is cancelled here, obviously. M equivalent VA squared goes down here. And VB over VA squared is B over A, so M B over A squared. So the equivalent mass is at A is M. And the equivalent K, as you see here, is K, as I have shown here. On the other hand, at B, you write the potential energy of the spring. Potential energy equals 1 over 2 K X A 1 over 2 and equivalent of B X B squared. So K equivalent at B is equal to XA squared K, which is XA over XB is A over B. So K equals XB equals so the equations are going to be for this one, let me write it here, B over A squared M XA double dot XA 0 would be the equation for this one. Okay. And for that one, this one, for the B equation, it will be M XB double dot plus A over B squared K XB. Okay. These will be the equations of, by the way, I didn't write it. The B coordinate, this has to be XB. XB is going upwards, defined as upwards, okay? XA is downwards. It is in order to keep this thing, this sign positive. All right. Any questions about this? So we can write the equivalent systems. As I have told you before, I am going to give you some problems on deriving the equations of vibrational systems, so that you can practice on them. So I will give you some problems on vibrations. Probably I will post them today on the class. Okay, so much for modeling. From now on, we assume that the model of the system is available. And from that point on, we are going to try to solve the equations of motion of the system, which is we will try to solve the differential equation. We will be solving, starting from the simple case, we will be solving differential equations for single degree of freedom vibrations. But let me, this thing has become too big, so let me just go to a new one. Okay, open a new whiteboard. And let's continue from the new one. So we will look at undamped free vibrations. We will take the simplest system possible, simplest vibrating system, a mass and a spring. Okay. Well, this is the equation of motion of this system is mx double dot plus kx equals 0, as you know. Well, since there is no forcing, free vibration, how does the vibration occur? It occurs due to initial conditions, okay? So you take this mass and displace it an amount of, let's say, this distance is, let's say, x0 or something. So x of 0, initial condition, is x0, and possibly x dot of 0 might be v0. These are the initial conditions. V0, now, you know, if both of the initial conditions are 0, then there will be no vibration. It will just stay stationary. We want to solve the equation of motion, but we will define something. First of all, we will modify this equation as follows: divide everything by m. It's the same equation. And we will define the natural frequency squared, omega n squared, as k over n, where omega n is the root k over n. It is defined as the natural frequency of a system. It is natural because it is it's a property of the system, and its unit is radians per second. It depends on the values of k and m, and it is the frequency of free vibrations. That is, if you pull this system and leave it, it will vibrate at its own natural frequency. So if I, for example, for this system, draw a coordinate axis like this. If this is x, initially x is 0. This is the time axis going downwards, let's say. So I take it from here. This is x0, the initial condition. Okay. If I leave this system, what will happen? I pulled it, I left it, then it will, you know, go back and forth, and with a certain period, and that period is dependent on the natural frequency of the system. It will do something like this over the time. And if there is no damping or friction, my drawing is not very good, but you can understand this is supposedly a sine wave, okay? And the period of it must be the same. It goes on like this. This is the period And the natural frequency is 2 pi over the period. Okay. It is also equal to root k over m, obviously, but this is from the so it just moves back and forth like this. Okay, well, it can be that, for example, you might have a pendulum like this. The natural frequency of a pendulum can also be defined for small vibrations. This is theta, this is L, this is T. It can have an M, but it doesn't matter. Here you have theta double dot plus G over L, theta equals 0. So that for the pendulum, the natural frequency is root G over L. So G is the gravitational acceleration. So for the pendulum, this has to be L, small case. Pendulum's natural frequency is dependent on its length, not on its mass. Okay, so it is the term in front of theta or in front of x is the natural frequency squared, okay? So this is omega n squared. Okay, so we want to solve the equation, the following equation. Since this is omega n squared, x double dot plus omega n squared x equals 0. Okay. Or you can say the second derivative is minus well, we want to find a function x so that its second derivative is going to be itself equal to itself times a constant, which is minus omega n squared. Well, what kind of functions have this property? It's kind of obvious, actually. You have to have a function. We will try to find a function whose second derivative is equal to itself. Well, times a constant. You take two derivatives and then you will get the same function. But this happens only in harmonic functions, actually, which are sines and cosines, okay? The second derivative of sine is another sine. Second derivative of cosine is another cosine, isn't it? For example, let me just say, let's say sine omega n t. The one, well, let's say x of t is this. X dot of t would be omega n times cosine omega n t. And x double dot of t would be minus omega n squared sine omega n t. We have found it, you see, which is, this is exactly the function itself, what we have assumed. So sine omega n t is one solution. Another possibility, we can take a cosine, x of t equals cosine omega n t. Take one derivative, minus omega n sine omega n t. X double dot of t would be minus omega n squared cosine omega n t. And we have found another function. This is x of t itself. So it obeys our original equation, this one. So this is one solution. This is another solution. Both are possible solutions. If both are possible solutions, and since this is a linear system, the general solution is simply the addition of these with some constants. You can put constants in front of these also. X of t equals, let's say, C1 times sine omega n t plus C2 times cosine omega n. You see, this is our general solution. Well, one thing is the problem here, which is C1 and C2. C1 and C2. Has to be determined from initial conditions. In short, I will use IC for the initial conditions. For example, let's look at the initial conditions example. Let's say that our initial conditions are as follows. X of 0 is x0, x dot of 0 is 0, let's say. Okay. In that case, we just substitute x of 0. We just substitute t equals 0 here. C1 times sine omega n t. When t is 0, this is 0. C1 times 0 plus C2 times cosine omega n 0 is 1. C2 times 1 is equal to x0. This is our initial condition. X of 0 is x0, which gives you this is 0. C2 times 1 is x0. So C2 is x0. We have found C2. On the other hand, x dot of 0 is, we will take the derivative of this. C1 omega n sine omega n of times 0, right? Minus C2. No, it's not a, this is not a sine. This is a cosine. Well, what do we get? It is C1 times omega n. But x of 0 was 0. X dot of 0 was 0. Because this term is 0. This is 0. Which gives you that C1 is 0. So our general solution is okay. This is the solution for this case. You see, actually, this is exactly this solution I have drawn here. It starts from x0 and oscillates like this, as you see. Now, the general case, when you have velocity, initial condition of velocity, the general case, where x of 0 is x0. And you might have an initial velocity as well. You can give an initial velocity to the mass, okay? Just, you know, initially you can give it might have a velocity. Let's try to find out the C1 and C2 values here. X of 0, which is x0, equals C1 times 0 plus C2 times 1 again. It's equal to x0, from which we get the same solution. C2 is equal to x0. Okay. Well, x dot of 0 is V0, as we know. That is given. It is C1 times omega n times 1 minus C2 times omega n times 0. So C1 omega n is V0, so C1 is equal to V0 over omega n. So the general solution is x of t equals V0 over omega n sine omega n t plus x0. This is the most general solution for a single degree of freedom vibration problem. If we draw this solution, what we get out of this is something like this. Let's say that I write x of, this is t, this is x. Okay. So we start from x0. This is the initial velocity, initial position at time equals 0. Now, initially, this thing has a velocity. So the over the time, it has this function is going to have a slope. So it will start like this. It is again going to be a sine and cosine. Well, excuse my drawing, it's not very good. But here, if you want to look at it, the initial slope equals V0. Okay. This is x0, small case x0. Okay. So it is a combination of a sine and a cosine. It gives you actually it is a sine wave or a cosine wave with a phase shift. Okay. So actually, we can write the solution as, another way of writing it is equivalent, as we will see. X0, this is capital, cosine, let's say. I could have said sine, it wouldn't matter, omega n t minus the phase angle, okay? Let's say that this is the A solution, and this is the B solution. And A and B solutions are equivalent, as I will show. Now, x0 is the amplitude. And this is the case. But what is capital case x0? Capital case x0 is the following. It is the maximum value of this. X0 is here, and here you have negative case x0. It is not equal to the small case x0. It is something else, as I will show. Okay, how do we show this? If you open up this using a trigonometric identity, you will get the following. X0 cosine omega nt minus phi equals, okay? Cosine, you see, x0, cosine A and cosine B kind of thing. This is cosine phi, cosine omega nt, plus x naught, x0, sine phi, sine omega nt. Well, look at this. This is something, this is another thing. So this is a cosine, and the sine added up together with certain coefficients. Well, what would those coefficients be? If these coefficients, if you look at the A equation, this can be, for example, small case x0, and this can be V0 over omega n. In this case, they would be equivalent. So you can write the following. Cosine phi would be equal to small case x0. Let's say this is our first equation. Now we want to solve for x naught and phi. How do we do it? First of all, if you divide, let's say this is 1 and this is 2. 2 divided by 1. If you divide 2 to 1, you are going to get tangent phi small case, let's see. So phi is simply tangent inverse of on top of that, If you square the first equation and square the second equation, okay, you are going to get you see cosine square and sine square terms are going to add up to 1. So you will get x naught is going to be small things x plus and that's another. So the free vibrations can
John,
be expressed. Sorry?
I have a question.
Yes.
Hujam, is there a difference between x0 on the left side and the x0 on the right side?
Yes, obviously. This is the initial condition, and this is the amplitude. This is what I have shown here. This is the initial condition. Okay. This is x of 0. Okay. This is the amplitude. One is small case, the other is capital case. You see, capital case x0 is larger than small case x0, or it might at most be equal.
Thank you, Hujam.
Okay. So you can use either A solution, this one, or the B solution, that one. As a matter of fact, you can also even use the sine solution. But the thing is, a sine and a cosine combined gives you a sine or a cosine with a phase shift. This is the importance. And the phase shift, as you see, is given by this formula I have outlined. By the way, if V0 is 0, if the initial velocity is 0, the phase shift is 0. And as you see, x0 is going to be x0. Because V0 is 0, you get. This will happen. The phase shift happens only when there is when there is a initial condition for velocity. Okay. But I will continue with damped vibration, but I guess it's better if we take a break here. So let's take a break. I'll continue in about 10 minutes. Okay, let's continue from here. Actually, it seems I have forgotten to stop the recording. It doesn't matter, I guess it will be a little bit long. So let's go one step further. We still have free vibration. With viscous damping. So we have added one more thing to our system. So we have a mass spring system, but just as in real systems, there has to be some kind of a dissipation, and we model that dissipation by a damper like here, E. Okay. So this is X of T. Our equation of motion now is mx double dot plus bx dot. This is our new term plus kx equals 0. With the initial conditions of x of 0 is x0, x dot of 0 equals 0. We need to solve this. And this is our viscous damping term. Okay, we will solve this equation. We will find the x value given the initial conditions. Well, you must have seen this differential equation before. We will assume the following solution. A constant c times e to the st. Let's see what this leads us to. Okay, we are going to get something. Well, let's take its derivatives. X dot of t, time derivative, is cs times e to the st. X double dot of t is cs squared e to the st. Substitute it into the original equation. If you put it back, you will get c m cs squared e to the st plus b c s e to the st plus k c e to the st equals 0, right? Or you can, well, c is common. What is common? What you can do is divide everything by m. So you get something like this: c s squared plus b over m s plus k over m e to the st equals 0. Now this is a 0. You cannot have c and a e to the st can't be 0. So this thing has to be 0. So c and e to the st can't be 0. So the thing in the parentheses must be 0. S squared plus b over m s. Whatever this s is, we don't know what this s is, by the way. We will find out. You might suspect it has to do with Laplace. Well, of course it is. It has to do with, it has connections with Laplace transform, but not exactly. Anyway. And this equation is actually called the, as you can guess, the characteristic equation, whose roots are the, well, we will find its roots actually. Solution of this equation for S, solutions, I should say, S1, 2. It's a quadratic equation, so you can solve it. It is just use the quadratic formula. So there are two possible solutions, S1 and S2, okay? So the general solutions, therefore, we had assumed C to the ST, as you might remember. So the general solution would be, for the differential equation, would be X of t will be C1e to the S1t plus C2 times e to the S2t, where S1 and S2 are given by this plus minus. S1 is the plus term, S2 is the given with the minus term. Okay. But we have a square root inside this solution. And we will see that if this thing inside the square root is like, it has the potential to be negative. So if, for example, b over 2m squared is less than k over m, the thing inside the square root would be negative. So the S1 and S2 are called, let's say, the roots of this equation. Roots will be complex conjugates. Okay. Well, let's look at all the cases here. For example, the simplest case is if you assume no damping, in which the B is 0, this reduces to free vibration with no damping case, okay? In this case, S12 would be, B goes away, B is 0, B is 0. Just simply plus minus square root of minus k over m, which is equal to, again, plus minus of, well, minus square root of a minus quantity. You put that minus as a j, which is, you know, where j is equal to square root of minus 1. And root k over m is omega n, as you know. S12 can be written as, actually, equals plus minus J. So omega n would be root K. These would be the roots of our equation. And you would have e to the j something, which by using Euler's identity, you can transform it to sines and cosines. Actually, all these functions are related. But let's find something else. So for the case of no damping, this is what we have. Let's define something. We will define the so-called critical damping. This is the case when the thing inside the square root is going to be 0. Okay, be let's say critical. So the square root term blah blah will be 0. So be critical over 2n squared minus k over n 0. Okay, in this case, we are transitioning from complex roots to real roots or vice versa. So if you pass it to the other side, multiply it with that. So we will have the critical squared will be 4 mk, or the critical would be 2 root mk. Okay. So this is the critical damping definition. Remember that we had omega n was equal to root k over n. We will define another parameter now. This is the zeta, the Greek letter zeta, the b over b critical. Okay, which is b over 2 root mk. This is called the damping ratio, and it is a dimensionless quantity. Now, I will show you that I can write our equation of motion, the original equation of motion, which is the following: x double dot plus b over m x dot plus k over m x equals 0. Okay. We know that k over m is omega n squared. What is b over m? B over m. Let's try to find this out in terms of the parameters I have defined. Let's try to find it out. B over m. Now b, I'll try to write it in terms of zeta. Okay. From here, b is equal to zeta times 2 root mk. Rather 2 zeta times root mk divided by m. But you have root m divided by m. That will give you 2 zeta times root k over root m, which would be 2 zeta root k over m, which is 2 zeta omega n, right? So v over m is 2 zeta omega n. So our equation of motion can be written as x double dot plus 2 zeta omega n s plus omega n squared equals 0. Instead of using v over m, k over m, we can use the following equation. This is much more convenient. Okay. Zeta is a damping ratio and it is dimensionless. That's the nice thing about zeta. And now from here, if you want to use this equation instead of that one, the characteristic equation can be written as s squared plus 2 zeta omega n s plus omega n squared equals 0. This is the characteristic equation. And the roots, which are of this characteristic equation, can be written as follows. This is much more convenient, as we will be seeing. It is the solution of this quadratic equation, minus zeta omega n plus minus omega n root zeta squared minus 1. Now this is, as we will be seeing, much more convenient for us. We will use this thing. Now, cases, depending on zeta, we will have different cases. The first one is the zeta equals 0, which is undamped case. Zeta equals 0 means v equals 0. Okay, there is no damping. We know this case, but let's the second possibility is zeta is between 0 and 1. It is called the under. Okay. The third case is zeta exactly equals 1. This is called the critically damped. And the fourth one is overdamped. Now, for us, the important case is this one, okay? The underdamped case. This is important for vibrations. Let me write this. In general, this is the most important case where you have oscillations in the system. And more realistically, most systems oscillate and the oscillations eventually die out. So underdamped is important for us. So let's look at that case more in detail. As we have said, the undamped results in undamped was S12 was minus plus minus J omega n. Okay. So let's look at the under case. So the damping ratio is between 0 and 1. And the roots of the characteristic equation are theta omega n plus minus omega n root zeta squared minus 1, as you see. But zeta is less than 1. So this thing inside here, inside the square root, is a negative quantity. So we will write this as minus zeta omega n plus minus j. Okay. Since it is a negative quantity, I will multiply it with minus 1. And the square root of minus 1 is j. Square root of. Now I will change the sign, 1 minus zeta squared. Since 1 is larger than zeta squared, this is the correct way of expressing it. Now there is something missing here. Sorry, let's base this. This is wrong. J omega n root 1 minus. Okay. Now we can define again one more thing, omega d, the damped natural frequency, as omega n root minus zeta squared. This is called the damped. This is the frequency of the damped oscillations. Okay. Again, this is again radians per second. So a damped system is going to oscillate with this frequency, not with omega n, but rather with omega d. Okay. As we will be seeing. So the poles, the roots, are going to be minus zeta omega n plus minus j times omega d. Okay, so we have complex conjugate roots actually. Okay. Let's try to find the solution to this. Remember that our solution, physical solution, x of t was c1 e to the s1 t plus c2 e to the s2 t. C1 and C2 are constants, doesn't matter. C1 e to the S1 minus zeta omega plus j omega d plus C2 e to the okay. So this is our solution. Well, we can do something about it. You see, e to the zeta omega n is common in both of them. We can write it as follows. X of t equals e to the minus zeta omega n t. Okay. C1 e to the j omega t plus C2. Okay. Here, the famous Euler's identity comes into the picture. Let's write this down. Euler's identity. Remember that e to the plus minus j theta is equal to cosine theta plus minus j. Okay, so we can write this following as follows. X of t equals e to the minus theta bracket c1 parentheses e to the j omega dt, so it is cosine omega dt plus j sine plus c2 e to the minus. Now that would be a minus, so cosine omega dt. Now a minus j sine omega dt. Close the bracket. But there are j terms, which I will write as follows. Again, e to the minus theta omega t bracket. Now, cosine terms are together, so you have c1 plus c2 cosine omega dt plus j c1 minus c2 now I will call this c1 plus c2 as a, and this j times etc c1 minus c2 as b. Now, in general, C1 and C2, since our equations are complex, eventually well, C1 and C2 can be complex, but since our solution represents a physical system, A and B terms must be real. So let me write this down. C1 and C2 can be complex, but A and B are real. So let me write the solution again. X of t equals e to the minus zeta omega nt times a cosine omega t plus b sine omega t. That's very interesting because remember we had what is this? This is very similar to the solution of an undamped system, okay? Similar to undamped system solution. Actually, it's exactly the same as the undamped system solution. And what is this part? You multiply it by the so-called exponential decay. So exponential decay, let's say exponential decay function, let's say something like e to the minus at function, something like this over the time. Let's start with one. So it just, a is like any constant, doesn't matter. but it dies out over the time, okay? So you have a sine and cosine terms multiplied by a decay function. So the vibrations, well, they start, but eventually they die out. Now, just as in the case of vibrations with free vibrations with no damping, we can write this thing as we can write this equation as, let's say, x of t. But instead of using a and b's and sines and cosine, I'll just use a simple single thing. X0 is the amplitude. And then there is a decay term, exponential decay, cosine omega dt minus the phasor. So this is the amplitude. This is the phase angle. This is the damped natural frequency. Damped natural frequency. Zeta is the damping ratio, etc., etc. Where I don't want to derive this, but exactly the same procedure can be used to derive the following. X0 is equal to square root of a squared plus b squared, and phi equals tangent inverse of b over a or a over b over a. B over a. Okay. So if you have a certain, let me try to draw this. X of t, supposedly. So you start from a small case of x0, initial condition, and there might be a v0 as well. So what you get is going to be, first of all, there will be the decay terms. The so-called decay envelope. These have to be symmetric. Oh, terrible. Okay, something like this. Okay, and then your vibrations have to stay inside this. And it becomes less and less and less and so on. So this envelope is x0 e to the minus theta. Now, this is the period of the damped oscillations, TD. And this has to be the same. This is also TD. This is also TD, although I couldn't draw it like it. TD is 2 pi over omega d, the damped natural frequency. So this is the where omega d is the damped natural frequency. Okay, so this is what we get when you have damped vibrations, when you have damping on the system. The damping dissipates energy, therefore you get less and less vibrations. But if you have, for example, in the case of high damping, you would have something like this, okay? But if you have low damping, this thing might go on for a long time. I couldn't do it. You know, this is low damping. So that the oscillations continue for a long time if you have low damping in the system. One more thing is that the solution, as you might remember, is x of t. The general solution is x naught capital e to the minus zeta omega and t cosine minus the phase angle. What is the phase angle and x naught equal to x naught? I'm not going to derive it because this is a long derivation, kind of, and it doesn't really matter. I'll just give you the result. Okay. And let me give you an example, and after that I will stop here, well, for today at least. Let's say that you have a system with 10 kilograms of mass. P is 20 Newton second per meter. It's 1 centimeter. X dot of 0 is, let's say, is 0. The natural frequency is root k over n, which is 4,000 divided by 10, which is 400. The square root is 20 radians per second. The damping ratio is E over E critical, which is E over it comes out to be 0.05. It's really low damping. And the frequency of damped oscillations is omega n root minus zeta squared, which won't be very different from the natural frequency because the damping is low, 1 minus 0.05 squared, which is 19.97 per second. You see that they are very close. The solution is going to be, for the free vibrations, it's going to be x naught e to the minus beta omega t cosine omega t minus the phase angle. Now x naught from this equation, since our initial velocity is 0, this term goes away, so it's simply small case x0, which is 0.1 meters. But the phase angle is not 0 because there is a, well, this is 0. Phi is equal to tangent inverse of. V0 is 0, but this term is not 0, so tangent inverse minus. Exactly. 20 times 0.05 e to the t, right? It is 2 points, it's a minus, minus is a plus, 2.86 degrees. But you can write it as 2.86 times, how do you convert it to radians? Pi over something like this. Yeah. So this is the solution, for example, for this case. Before we stop, let me do one more thing. If you have, well, I will always, look at the underdamped case. Let's look at the critical damping case as well. Damping where you have E equals B critical and zeta equals 1. The root S12 is going to be minus zeta omega n plus minus j omega n root 1 minus zeta square, as you remember. But when zeta is 1, this term goes away. So you have S1 equals S2 equals minus omega n. So you have repeated roots. So the solution x of t is going to be, this is a little bit complex, but something like this, omega n t. It will be, and if you have x of 0 is x0, and x dot of 0 is v0, in this case, x of t will be, in general, x0 plus v0 plus omega x0 t e to the minus zeta. No, there is no zeta, zeta is 1. Omega n t. So with the critical damping case, you have, this is not a vibration anymore, it is just a something like this. The motion starts from here and it just comes back here. So this is x0, the slope is v0. This is x of t. This is t. So this is, you get the fastest non-oscillatory response. So the critical damping is used, for example, in door closing mechanisms, because in that case, the doors close without any oscillation. So you try to get critical damping. So this V0 is the initial slope. X0 is the initial position. But I don't want to spend too much time on critical damping or overdamped systems because they are not really that important in vibrations. So, okay, so much for today. I will continue with other examples, but I guess our time is up, so I have to stop here. I will continue with the fourth. We looked at free vibrations today. We will look at forced vibrations the next time. Okay? So if you don't have any questions, that's all for today. Any questions?
Hocam, before you leave, can I ask a short question?
Okay.
Duyabiliyor musun hocam beni?
Duyuyorum.
Bu dönemin sonuna kadar online yapacağınız için dersleri, odanızda da feedback almak için midtermlerde ya da başka bir konuyla alakalı herhalde mümkün olmayacak. Olur mu ya da onu
Pek
sormak.
olmayacak herhalde, evet. Yani biraz zor gözüküyor, evet.
Tamamdır hocam.